Good afternoon, everyone. My name is Stina, and the work I'm going to talk about is deep learning-based least sphere decoding for faster-than-Nyquist signaling detection. So I will first talk about the faster-than-Nyquist, what is this, and the introduction, and then the detection of the faster-than-Nyquist signaling, and I will go then for the approaches, the equivalent FDN signaling system model, and our deep learning-based least sphere decoding algorithm, and I will show you some results. So in future communication, the bandwidth is so much important because in future we have lots of drones and lots of IoT stuffs. So the bandwidth in future will be so important. And the thing is, if we can increase the data rate without increasing the bandwidth. So this is a very important goal. So one of the promising approaches is using the faster-than-Nyquist signaling, which means that we are not sending the signals at the rate of the Nyquist. We're sending them faster than and with the rate of 1 over tau t. So the tau here, we can call it acceleration factor. So for example, in the right side, you can see the figure. The top figure is when we are sending the signals with the Nyquist ratio. So as you can see, the colored lines are the symbols. So as you can see, there is no interference between the symbols. So, but when we send those symbols with the for example, with the 0.8 acceleration factor, so obviously we will have some interference between those symbols. So we can increase the data rate, but at the cost of some introduced ISI. ISI I mean the intersymbol interference. And one work, the muzzle has been shown that we can set the tau 0.802 and still can get the data without any deterioration with the error rate, but this comes at the cost of removing the ISI. So this is a challenging part. So the faster-than-Nyquist signaling detection, the transmit signals in this system model can be summarized as follows. So we have some BPSK symbols in our work. So it will be +1 and -1. And we have some pulse shapes. So in our work, we choose the pulse shapes as a root raised cosine pulses, and they are T orthogonal root raised cosine. So as you can see, the system models are here. So when we do the fast FTN signaling, when we send these signals at the faster-than-Nyquist rate, as you can see, we are sending them with the tau t. So in the receiver side, when we sample those at the rate of tau t, so we are expecting to have some interference because our pulse shapes is a T orthogonal pulse shapes. So when we are sampling at the tau t, so we are expecting to have some interference. And also we have a white noise here, so we don't consider the channel here, so we just have a white noise. If we have a white noise and then we sample the white noise at the rate of tau t, so also we have another issue that is we are dealing with the colored noise. So with the colored noise, we will get a very poor performance in comparison to white noise. So the thing is, we are going to design we have a two approach to remove the colored noise. So we have to design an exact whitening noise filter, which designing the causal and stable whitening noise filter is very, very hard and challenging, and also especially for small number of tau, when we send the for example, 0.5 when we send them faster. So it's so challenging, and we cannot find very exact whitening noise filter. But we have another approach, which is equivalent FTN signaling model. So the thing is, instead of sending, so as we said, we have a pulse edge, right? We are sending those with the pulse shape edge. So we can approximate the pulse shapes with the sum tau t orthonormal pulses. Is approximated as the sum of tau t orthonormal pulses. So as you can see in the right picture, this is we have three lines: dash lines, solid line, and dot lines. So the dash lines are the V pulses, which are the tau t orthonormal pulses, and the solid line is H, and the dot line, which you cannot see clearly because the dot line are the approximated one, which is exactly matched on the solid line. So as you can see, it's a very clear match. So we can just approximate. We have a very good approximation of pulse H with the sum of tau t orthonormal pulses. So we can reformulate with this model, the FTN signaling. So the transmit signal will be something like this. So we are sending with the tau t orthonormal pulses here, and at the receiver side, so after sampling, actually, we have some real values plus some noise. In this case, the noise here is white noise. We don't have a color noise because the pulses here is a tau t orthonormal pulses. So let's moving forward. Yeah. So as I said, in the receiver side, we have some equation, the matrix equation. We can express as a matrix equation like this. For the sake of the channel decoders, we need to generate the soft output of the received signal. So we have to use the maximizing a posterior probability. So the formula is as follows. So I'm not going to explain the details of this formula. So and then I just want to make sure. I just want to mention an important point about this formula. So if we rewrite this formula using the Bayes theorem, so we are dealing with equation like this. So as you can see, the x vector is a transmit bit block. So as you can see, we have to search over all possible lattice points, all possible vector points for x to find the exact the maximizing a posterior probability, which we are expressing as a log likelihood ratio. To find it, we have to search over all the lattice points. So that we will have a 2 to the power of n lattice points because we are considering the BPS case. So we have just positive 1 and minus 1. So we have a 2 to the power of n points. And also inside the exponential function, we have the calculation of this function. It takes n square. So at the end, we are dealing with the 2 to the power of n times n square. This is a very huge complexity. So for example, if we transmit the block with the 25 symbols, we are dealing with the 20 billion operation. So it's totally not feasible. So the idea that we are using in the next slide will be the likelihood function inside this equation is expressed as this equation. So as you can see, the likelihood has exponentially related to the distance of the received vector and the skew lattice. So if we consider not the lattice points, if we consider just close points to the vector y, so we can still have a very good approximation of the LLR values, log likelihood ratio values. So the thing is, our approach is limiting the search area over a circle centered at the received vector y, and then so we define a predefined NL number of points close to the vector y instead of the lattice point. So the complexity here will be NL times n squared. So in our case, we set the NL equals to 32. So it will be 1500 operations, which is much less than 20 billion operations. It's much faster than. So the thing is, searching over the lattice point when we have a received vector, we have a sphere decoding algorithm, which when we have a received vector y, we imagine a circle centered at vector y, and we have an initial radius r, and we search over all the points inside these circle or sphere. But in this figure, you can just see the 2D figure, but in the reality, this is a hypersphere because the dimension of this matrix will be 25 by 25. So we will dealing with the hypersphere in the 25 dimensions. So yeah. These algorithms called least sphere decoding. So the least sphere decoding, as I said, we set the initial radius and we search over inside the radius of the hypersphere. So the thing is, if we set the initial radius too small, so we may not find any lattice point inside the hypersphere. Or if we set the initial radius very high, so we don't get anything, so then we just search over the lattice point because we set the initial radius very huge number. So again, we just have another exhaustive search. So the thing is, we have to find the initial radius that guarantees we have just NO number of points inside the hypersphere. So the idea is that we are estimating that initial radius, as I said in previous slide, that guarantees to include a predefined number NL points inside the hypersphere. So we are going to learn this radius with the deep learning methods. So we are using the recurrent neural networks. And the reason behind the using recurrent neural networks is that, as I said, in Faster-than-Nyquist, there is an intersymbol interference between the previous samples and other samples, right? So, and we know that the recurrent neural networks are very promising in estimating the sequentials data that they are relating to each other. Yeah, there's lots of other structure of recurrent neural network, LSTM, long short-term memories, and GRU, but we get the good result with just a simple recurrent neural networks, and we just use those recurrent neural networks, which is the first. We have a 3 hidden layer. The first 2 layer is a simple recurrent neural network with 128 units. And followed by a dense layer. So the input is we will give the network the received vector, and we at the output we get the estimation of the radius. Simple. So as you can see, the algorithms are here. So we're estimating the radius with the neural networks, and we go to run this least sphere decoding with that initial radius. If we find the NL lattice points inside the hypersphere, we terminate the algorithm and we go through the calculating the log likelihood ratio for those bits. And if we didn't find it, we increase the radius by a value of by this value, which is the standard deviation of all the estimated radius during the training process. So yeah, I'm moving forward to show you some results. So as you can see in this figure, we plotted the number of the points, lattice points, inside the hypersphere when the blue ones when we are in our algorithm, when we choose the radius based on the deep learning approach, and this orange ones are the original LSD algorithms. So as you can see, the number of the lattice points inside the hypersphere, which is directly related to the complexity, will be, for example, in this case, at the low EB over noise or low SNR will be 10 to the power of 2. In comparison to the original LSD, it will be 10 to the power of 5. It's a huge difference. So in the lower small number of EB over noise. And when we go forward, as you can see, the number of the lattice point inside the hypersphere with the gap will be so small because we will have a very not very significant noise, so that's reasonable. And these figures are for the when we set the acceleration factor 0.6. And there's another comparison, which is we counted the floating operation points, which is directly related to the operation points for the CPU. So we call it flops. So as you can see, the proposed deep learning based least sphere decoding has a 3 order of magnitude better than the original least sphere decoding, and also in high SNR we have just an order of magnitude better than original least sphere decoding. So, and another figure here is showing, so here we have, for example, the green one, when we don't have an ISI, so where the acceleration factor is equals to 1, so we don't have any interference, and we just have a white noise. So as you can see, the green one is when we don't have an ISI. But if we set tau at the range of 0.74, the solid line with the square, so as you can see, they're so close to each other, no spatial gaps, and we have the same bit error rate, while we are saving spectral efficiency, 35% saving spectral efficiency, because we are sending the data faster at the rate of 0.74. So, and also you can see the solid line with the star when we send data faster than these values, for example, 0.6. As you can see, we have this one. So when we do the, also we plot when we apply the convolutional code to those, and and again running the deep learning based least sphere decoding, and so you can see we can have we obviously save 1.5 dB at the bit error rate 10 to the power minus 4. We can save 1.5 dB here, and also another 1.5 or 1.4 dB here too. So that's it. Thank you. So this work has been accepted in IUVTC Spring Conference. So you can check this out at the archive too. So thanks.
Yeah, thanks for the talk. And any questions from the audience? Okay, so yeah, we have some comments and questions from the audience. The comment actually is that I found it a little bit difficult to follow what was the introduction and what was your work. For example, like a method. That's the comment. And the question is what programming language or software did you use?
I use the Python. So all the things is implemented by Python, and also the neural networks. I use the TensorFlow and Cross library. So yeah, it's totally Python.
Okay. Yeah, I have a question. In slides page 10. Yeah, you show the result actually at the low end and the high end, right? The result is different, right? Why? Yeah, why the result is different at a different scenario?
Because I can show you here in this figure. So this is if we assume that this is a vector y, so it should be one of these which perturbed by white noise. So at the low SNR, so we will at the high SNR, so the vector y is so close to one of these. So the estimation radius and with the original algorithm of least square decoding and our proposed algorithm, because this point is so close to the one of these lattice points, so there will be no spatial gap. But if we have in small EB over noise or SNR, so we have a very edge noise. So the received vector will be so far away from the transmit signal. So in this case, the hypersphere should have the big radius. So that's the reason there's the gap between the highest and lowest center.
Yeah, and also on page 8, you show that actually this deep learn RN, there's quite a different approaches, right? And you choose the one you show on the slide. I'm just wondering that do you know why this one is more effective and
the recurrent neural network?
Yeah.
As I said, the recurrent neural networks are promising with the sequential data. By sequential data, I mean, for example, we have a sequence. We have a sequence which each data inside the sequence has some relation between the symbols after and before or other symbols. So the recurrent neural networks are good to extract those features. For example, as you can see in this figure, and when in the there is a some, as you can see, there is some interference between the next and next symbols and other symbols for this symbol. So there is some relation between the previous and next symbols. So that's why I choose the recurrent neural network structure to extract those features better. And also I use the just fully connected dense layers. So, but the result for the recurrent neural network is a bit better in terms of the loss functions and stuff. Yeah.
Okay. Yeah. Okay. Good. Yeah. So thanks for the talk. Yeah. I just give a few comments. Okay. Yeah, basically, the part I like actually is at the very beginning you give the motivation, right? And so I really like that part. You know, this is a very interesting. For example, sometimes when you go to a conference, you see that sometimes a good talk. Sometimes they just at the very beginning they give a first slide show that okay, what's the problem? Okay, in this field, and then what people have done and why they want to do this. And that will attract the audience interest, right? They know immediately, oh, okay, well, this is what they want to, why they want to do it, right? And how they, what they're going to do, right? And so I think that's the really good part. And so this is not only for you, also for all the audience, actually. If you go to a conference in the future, and if you can somehow, that's a kind of technique, you know, at the very beginning, you highlight that, okay, this is what the problem, okay, and I think that's very, very useful and interesting. That's the good part, okay. In terms of the overall, still, I feel I think I have the similar comments with the audience. Actually, is that at the beginning of the motivation, right? And if you can give a little bit better the overall picture of your work, right? And for example, what kind of application there are, and what's the current status, and just tell a little bit more about those kind of Nyquist sampling, right? And with this Faster-than-Nyquist, if you give a little bit more explanation, you know, and then the people that not in this field, and they can sort of understand what you're talking about, okay? And then it's easier for them to follow the next the rest of the talk, you know. The problem is that if you are in this communication field, and it probably is this common knowledge, right? But for some of the audience, if they're not in this field, they could easily get lost at the very beginning, okay? So yeah, give a little bit bigger picture, and give some more explanations, like what I mentioned at the very beginning for the comments from another student, and that really will help you your presentation. Okay. Anyway, I think the talk is very good. It's just like you always have to think about the audience. Okay. For example, if this is one is for the conference, for some of the conference, actually they're all very specific area, research area, the most of the audience and sort of expert in that area, so you don't have to give too much background. So you have to think about which kind of conference you're attending and what kind of knowledge level of the audience. Okay, so it's always very important that you think about that before you give the talk. Okay.
Yeah, sure.
Yeah, Jennifer, and also you can. I saw that you only use 13 slides, right? Basically only 10 slides. So you can use a little bit more slides and give some examples and something like that, right? And they'll always help the audience. Okay. Anyway, yeah, I like the style. I mean, the diagrams and the result. It looks very interesting and well prepared. Okay, thank you.
Thank you.
Only in this presentation, I'm going to talk about wireless capsule endoscopy image classification using SVM classifier. In this presentation, I'm going to introduce some basic knowledge in this field, and then I will talk about the type of data that we use in this project. Thirdly, I'm going to talk about how we can extract the features that can be used for this classification, and then I talk about support virtual machine that I've used as a classifier to be used for classification of the WC images, and finally we have some simulation of this. Okay, as you can see here at the yeah, you can see here there are some medical pills that can be used for endoscopy instead of doing some surgical operation that we call the technology here wireless capsule endoscopy. That is a video technology approach to detect diseases like bleeding in small intestine. These type of pills send some images, some RGB images to receiver, and we get these images and do some processing to find whether there is some abnormality like bleeding or not in the images. Actually, the experts such as doctors can use these RGB images to detect whether there is a bleeding in the image or not, but computers need to detect just the bleeding parts of the images, so we need to do some color scheme conversion that can help the computers to detect these abnormalities. Um, as you can see here, the original image that we get from the pills are something like this. These red pixels are bleeding parts of the image that we can say that this is abnormality in the body, so we are going to detect these parts. Actually, as what I said before, we need to do some image and color scheme conversion. So we convert the RGB images to YIQ, that is a well-known color scheme. By doing this and doing some Q value thresholding, we can get these images, and doing some morphological and duration operation that are well known in this field. We can get this image, and as you can see, as we compare the image A and D, we can see that the D image, actually in the D image, we extracted the pixels that are related to the bleeding pixel in the original. The type of data that we have used in this project are from a well-known data set named KVASURE that is publicly available on the internet. These images are RGB images, and the number of pixels are 336 and 336 for each plane. These images include some bleeding. Each image may include some bleeding or not pixels. As what I said before, these bleeding pixels can be easily seen by the doctors, but they are not appropriate for computer-based analysis. That is what we are going to do. So we need conversion from RGB to YHQ. After doing this, I mean, after doing the conversion from RGB to YAQ using these metrics, we can get the images um, like this. That's as what I've said before. These pixels are related to the bleeding part of the images. After extracting the bleeding part of each image, we are going to convert another conversion just only on the region of interest that are the bleeding pixels. This conversion is RGB to CMYK. This CMYK is another uh, color scheme, another well-known color scheme in this field, and this, using these formulas, we can convert the RGB to CMYK. After doing this, actually, it's worth mentioning that in this part, we are just applying this conversion to the region of interest, I mean, to the pixel that we get after doing the YIQ and Q thresholding operation. We use four features that are C mean, M mean, Y mean, and K mean. These statistical mean features will be used as our feature to classify the bleeding and non-bleeding images. As you can see here, this figure shows how these features are useful to be used to classify the abnormal and normal images. As you can see here, each of these figures shows um, um, the four features that we use. For example, this one is the C-mean that we extracted from the image. The green circles shows the non-bleeding images, and the uh, red circles shows the bleeding images. And as you can see here, almost all of these features can separate the bleeding and non-bleeding images. There's another result that shows these features are really appropriate. This histogram shows the uh, actually the distribution of the feature. For example, these uh, A and B images shows the yellow mean for bleeding and non-bleeding, and as you can see here, the distribution is from 150 to almost 220, and for the non-bleeding, it's from 140 to almost 190. And as you can see here, almost all of these features can be used to uh, classify our images. So after that, we extract the features. We are going to use support vector meshing. That is one of the machine learning algorithms in the class of supervised learning. Actually, we have n images, and each for each image we extract two features. As you can see here at the right of the screen, this is the mean of the Y, mean of the K, and mean of the M for our data set, and this shows our class. For example, one shows that the image is abnormal, and two shows that the image is normal, and means there is no bleeding pixel in the image. So for each images, we extract two features. For example, we can use mean Y and mean K, or we can use mean Y and mean M, or mean K or mean M. And we use two features for ease in the visualization. And actually, the Y and K have less overlaps, so these features can be more useful. To apply the support vector machine, we divide our data to two groups of data sets. The first one is training, and the second one is test. data set, I've used Fit CSVM, that's a toolbox in MATLAB to apply SVM on the data, and finally test the model using this. This is our model, and using this model, we test our model on the test data. Um, the left image shows our objective function, and as you can see here, this support vector machine try to extract a hyperplan that can classify the two class. This is the final hyperplan that we get, and some of these points here shows the minimum of the objective function here. We can see that this is the green one is the region of, for example, our class 1 data. The red circle shows the data of the class 1 data, and here shows the data of the class 1. As you can see here, this machine learning algorithm can easily classify our data to two groups. There's some other results, and as you can see here, these are the results of the work, and actually these are separate vectors that can be used as the features for further classification. Actually, there is a comparison between the method and some of the works in the literatures. Actually, in this method, we have used only 4 features to classify our images, and as you can see here, we get a good accuracy. This figure shows the test set. The circles are related to the test set, and the cross shows our predicted label of each data set. And as you can see here, we can easily investigate the class of the data. These 1 and 2 shows the class of the data. And thank you.
Okay. Yeah. Thank you for the presentation. Any questions from the audience?
Thank you. Can I have a question?
Yeah, go ahead.
Yeah. Thank you. Very good presentation, Omid. I wonder, you said you used a support vector machine with the linear kernel, and I wonder if you have tried the support vector machine with the nonlinear kernels or polynomial kernels, and I think it might be you might be get better accuracy because the way you're extracting the features, it's obviously there will be a nonlinear relation between the classification and stuff like that. So I just wonder, have you ever tried the other kernels or not?
Thank you for your question. Actually, there are 3 types of, for all of the audience, there are 3 types of kernel that we can use for SVM. The first one is linear, that I've used this kernel, the polynomial and radio-based function. Actually, based what I have observed from my test, I found that using 2 of these features can easily separate the data. And as you can see here, let me show you this slide. As you can see in this slide, actually most of our data can be classified using a linear. Actually, that's the fact that I didn't use the nonlinear data. I know if we just use one feature, for example, in this slide, there should be something nonlinear to classify the images. But if we put the, for example, two of these data sets together, the images, the features can easily be separated using a linear kernel.
I got you. Yeah. Thank you so much.
You're welcome.
Okay. Thank you. Any other questions from the audience? Okay. Yeah, I have one question actually. I saw that the result looks actually very interesting. I just wondering when you have this data, you need to train the data, where the data database and what kind of data set you are getting from. It's a standard benchmark or?
Actually, I've used this data set. It's a well-known data set. This data set includes so many video for this field, but there is no actually hint for extracting features. I just um, searched through the literature. I found that these features are really usable to detect the black pixels, I mean darker pixel in an image. As you can see here, these pixels that are bleeding pixels are darker than the other pixels.
Okay, okay. I just wonder, for example, if you use some other type of data set and how it's going to affect your result. Have you thought about that? Or?
Actually, I've used just one video frame of this data set, but based on a theoretical assumption, I think that might be work because the fact that is behind of this feature extraction is that we can actually get some, as I've mentioned before, darker pixel in an image. And bleeding pixels actually are darker than other non-bleeding pixels.
Okay, okay. Okay. Yeah. Thank you for the presentation. Yeah, I think it's very good presentation. Yeah, I just want to give a very brief comment. Yeah, it's very good, and a couple of comments. One actually that I saw that sometimes in your presentation, not only you, right, and in your presentation, sometimes you have to use equations. And eventually for those complicated equation, and it used to be, yeah, we have some student have similar slides. And so, yeah, if you have those equations, and you have to be very careful, okay, unless it's super important in your talk. And because when you have this very complicated equations, and if you don't explain it well, it just really just confuse the audience. Okay, so when you think about putting equations in your talk, you have to be a little bit careful. Okay, so make sure that it's first is very important for your talk, and the second one is how to make sure that really people can follow that equation and know what basically the equation is about. Okay, otherwise it just it really doesn't serve the purpose. Okay. So remember that the talk is really just try to make people understand what you are doing, right? Instead of, so that's very important. Okay. Other than that, I think it's I really like you have a lot of pictures, and that actually shows the effect and the result, and also in the your result part with those diagrams, it works really well. Okay. Okay, I think I will just give a very brief comments at here. And today, actually, I'm very happy that from audience, and we keep have some questions. And I just want to really stress that one. It's very important that when you're sitting a seminar or in a conference, when you listen to a talk, you always try to come up with some questions, okay? And remember, think about it. For example, if you give a talk and people sitting there without any questions, it's kind of embarrassing, right? Even if sometimes you think you're very good to talk, but nobody want to ask questions, that's kind of embarrassing to the speaker, right? So it's very important that
As Professor mentioned, so today I'm going to talk about a modulation technique, which is known as spectral option modulation on conjugated spectral zero. So in this,
you may want to play your slide.
Yeah, sorry.
Yeah.
Yeah. So in this presentation, I'll go over the introduction, which will be followed by the discussion of the technique on which my modulation technique is based on, and then I will go over the proposed modulation technique, which will be followed by the detection, simulation results, and the conclusion. So future IoT or Internet of Things applications, such as telemedicine, factory automation, etc., they will be very delay sensitive, and they need to meet the requirements of ultra reliable and low latency communications. So because of the latency requirements, the URLLC necessitates the use of the short data packets for the communications as compared to our and opposed to the conventional communications which use the long data packets. The short data packets can be assumed as the small packets that carry the transmit information. So in the wireless transmission, what happens is that when the transmit signal is transmitted through the wireless channel or the environment, so it kind of reflected, diffracted, and scattered because of the several obstructions like building, trees, etc. So this kind of phenomena, which we call channel effect, it results in multiple copies of the signal being received at the receiver. And these multiple copies interfere with each other and degrade the quality of the transmitted signal. And this whole phenomena can be modeled, like we model this whole phenomenon in the communication as the convolution between the transmitted signal X and the channel H. So in the conventional communication, which uses the long data packets, so what we do is that along with the transmitted data or within that packet, what we do is that we send the known symbols called pilot symbols along with the transmitted data to learn the channel. And with the help of the information that is acquired from those pilot symbols, we try to cancel the effect of the channel by using like different techniques like equalization, etc. So, but the problem in short data packets is that like we cannot use the pilot symbols. I mean, we cannot send the pilot symbols along with the information that we need to transmit because as our data packet size is already small, and if we are sending a known information along with our data, so it will severely degrade the spectral efficiency of the transmission, which means that our packet size is already small, and we are also sending some known data to learn the channel. So like we are not utilizing the available space properly. So using the pilot symbols kind of severely degrade the spectral efficiency of the transmission in the short data packets, and also in the applications such as those I mentioned, the wireless transmission will be sporadic. So it is possible that between the true transmission, the channel state may change, and we need to acquire the channel information with every transmission. So it will cause further problems. So A modulation technique was needed for the shared data packets, which kind of perform the detection of the transmitted signal without the knowledge of the channel or without the usage of the follow symbols. So this technique a novel technique was recently proposed known as modulation on conjugate reciprocal zeros, which performs the detection without the knowledge of the channel. So coming to the block diagram of the proposed technique, which was on which my technique is based on, uh, is that if we have a bits of data here coming in, so we map these bits onto the zeros in the Z domain, where Z domain can be think of the Laplace equivalent for the discrete time signal. So we map the bits into the zeros first. So if we have a 7 bits that we need to transfer, so what we do is that we map each bit on. So if you have 7 bits, so we will divide first the circle in the Z domain into these 7 sectors because we have 7 bits. So and we're gonna map each bit into one sector, and as the bit can be 1 or 0. So the way we'll do mapping is that if the bit value is 1, we're gonna modulate it onto the radius r, and if the bit value is 0, so we'll modulate it onto the radius 1 over r. So here in the black ring, I'm showing the radius r, like the black outer ring, like it represents the radius r, and the inner black ring represents the radius 1 over r, and the red ring represents the unit circle. So as my first bit is 1, so I will modulate it onto the first sector, and as this value is 1, so I will gonna modulate it onto the radius r. Coming to my second bit, as its value is 0, so like I will modulate this second bit onto the second sector at a radius of 1 over r because the bit value is 0. So based on that, we kind of map all the bits to the zeros, and then we generate the coefficients corresponding to these zeros that we kind of map. And then it will follow the regular communication that we map those coefficients that we generated. So here we have like 7 zeros. So we will have 8 coefficients, and we modulate those onto the transmitted pulses, which will be transmit every t. And the reason we transmit this as every t is that like we kind of following the Nyquist criteria, because these pulses that we transmit, they are orthogonal at the interval of t, which means that if they are transmitted at every interval of t, they won't be interfere with each other. So like if we kind of transmit these pulses faster than the interval of t, then we have the additional interference because of the pulses. In addition, I mean the interference in addition to the channel. Then at the receiver side, we'll follow the normal mesh filter, which is usually present in the communication system, and then we'll sample the signal at the interval of t. But at the receiver side, we will kind of receive a long sequence of polynomial as compared to the sequence of the polynomial. I mean, the sequence of the coefficients that we transmitted. And this is because as I mentioned in the introduction, that we have the convolution between the transmit signal and the channel. So because of that, we're gonna receive the a longer polynomial at the receiver. And if you see zeros, the zeros of the receive coefficients or polynomial. So like if zeros are shown in the white, so like as we only transmitted 7 zeros, but like here we have 10 white received zeros, and it is because in the Z domain, what the channel does that instead of convolution, like its result is that it introduced the additional channel zeros in the Z domain, which are shown in the green. So like here by black, I'm showing the actual location of the transmit zeros, and by green, I'm showing the actual locations of these channel zeros. So like white 0 represent what we receive, and these zeros correspond to the transmit zeros, and the channel zeros plus they're disturbed by the noise. So the way we will perform the detection without the knowledge of the channel is that as we know that we have received 10 zeros instead of 7, but we know the location of like that with 7 zeros we could have transmitted based on the code book. So we don't need any information about the location of the channel 0 to perform the detection on the transmitted 0. So as I will explain later, so based on the code book that we have, we kind of detect that which of the 7 zeros that were transmitted in this case. So once we perform the detection, we will kind of demap the, once we detect the zeros, we will demap those zeros to the bits. Coming to my proposed technique, so what we do is that we kind of follow the same transmitter, except that we are kind of transmitting the transmit pulses even faster. Like meaning we are not following the interval of t, rather we are transmitting the transmitted pulses at an interval less than t. So here by tau t, I'm representing the factor which is kind of less than 1. So it means that as we violate the Nyquist criteria, it means that we will have the interference between the transmitted pulses. So what it does in terms of the zeros is that it kind of adds additional zeros. So here again, the white zeros represent all the zeros that we receive. So some of those zeros correspond to, again, the transmitted zeros, which are shown in the black, and the channel zeros, which are shown in the green. But here we can see that we have, like by pink color, I'm showing the actual locations of the zeros that are introduced because of the ISI. So a lot of the zeros that we receive, like they will be introduced by the ISI. So we need to perform the detection of the 7 transmitted zeros, um, uh, given that we have received a lot of zeros. So what we did is that we introduce a widening filter to cancel, as we know the position of the ISI is 0, so we introduce a widening filter to cancel some the inner zeros which are introduced because of the ISI. So after widening filter, when we remove half of the zeros that are introduced by the ISI, so we'll again perform the detection. Like we'll try to find out that which are the 7 zeros that were transmitted based on given that we have received huge number of zeros. And once we perform the detection, we kind of demap those into the bits. So here I'm just showing like the clear kind of picture that what widening filter does. As we can see, there are like a lot of inner zeros here before widening filter. So this is figure before widening filter, but after widening filter, we kind of remove all those inner wide zeros which correspond to the ISI. So like here we kind of reduce the number of zeros that we receive, and now we're going to perform the detection on that. So in this figure, I'm just showing the code book which shows all the possible zeros that can be transmitted. So as we had the 7 bits, and from each sector, we had 2 possibilities because if the if the bit value was 1, so we could have transmitted this 0 with a radius r, and if the bit value is 0, we could have transmitted this codebook 0 with a radius 1 over r. So like from each sector, basically we will have one possibility that out of these 2, we only transmitted 1 0. So same is the case for the second sector. So here this is just the codebook for us to help in determining this is the codebook to which helps in deciding which were the transmitted zeros. So here I'm showing the detection process. So again, the relation is kind of pretty same. So black zeros represent the transmitted zeros, green circles represent the channel zeros, and white circles represent the received zeros, which are disturbed by the noise. And here I'm just showing this for the easier understanding. I'm not showing the case where we have the ISI. It's just because I'm just going to show how we'll perform the detection in presence of the extra zeros. And here in the blue, I'm showing the codebook zeros. So the way I'll perform the detection is that as we have received 10 zeros, so first we will going to classify each of the 10 zeros into one of the sector based on its distance from the codebook zeros. So we'll measure, for example, if this is a received zero and we want to classify it to some sector, so I'm going to measure its distance, the distance of this received zero from all the codebook zeros. And I can see that this received zero is closer to one of the codebook zeros in this first sector. So I will assign this received zero to the first sector. Same is the case with this zero, like the distance of this zero was closer to one of the codebook zeros that are in the second sector as compared to the distance from the codebook zeros in other sectors. So that's why the received zero was classified in the second sector. So once we classify all the received zero into these sectors, so we know that as we have extra zeros, so it's highly possible that a sector will have more than 1 0. But at the end of the day, we also know that each sector can only contain 1 transmitted zero. So we will only pick 1 transmitted zero from every sector based on the minimum distance again. For example, in the first sector, we have 2 received zero. So we'll compare its distance from the 2 codebook zeros that are possible in this sector, and whichever zero among these 2 zeros was found closer to one of the codebook zero in this sector, so we'll decide that that was the transmitted zeros. So for example, this zero is closer to this codebook zero as compared to the distance of this zero from this codebook zero. So we'll say that this was the transmitted zero and it is disturbed by the noise. So we're going to estimate it from this zero. In the second sector, again, like we received 2 zeros, but we can see that this zero is closer to this codebook zero as compared to the distance of this received zero from any of the codebook zeros. So it'll say that this is the transmitted zero, which is basically we receive actually this. So it is disturbed by the noise. So this is the actual transmitted zeros. So it will going to indicate like which bit we transmitted from the second sector or the second bit. Coming to the third sector, we only receive 1 0, and you know that it is closer to this transmitted zero. So it's kind of very clear that this is the transmitted zero from the third sector. So that way I like that way we can perform the detection without the knowledge of the channel. So in the so here I'm just showing the simulation results, which shows the error rate versus the SNR, or the power that we need to spend to get a particular error rate. For example, in here this curve represents the actual MOXIE, and this curve represents like my proposed technique. So to achieve the error rate of 10 to the power minus 2, like in our technique, we need to spend like 5 dB more power as compared to the original MOXIE to get more data rate. I mean, to transmit more data at a smaller k, when like we have k equals to 7, which means when we are transmitting 7 bits. But like when we are transmitting 40 bits, so to achieve an error rate of 10 to the power minus 2, we only need to spend like 1.5 dB more power as compared to the original MOXIE. So here, I mean, results are pretty good for the higher K, because at the expense of 1.5 dB, we are kind of improving the data rate because we are transmitting the pulses faster. So here, when my tau value is 0.9, so it will result in a spectral efficiency gain. So as 11%, which means like, and the spectral efficiency is kind of bits per unit, bits transmitted per second per hertz. So like here we have like 11% spectral efficiency gain at higher value of when we transmit high number of bits. So coming to the conclusion, the proposed technique, which is called SE-MOXIE, is an spectral efficient blind modulation scheme for the facial IT applications, which will use the short data packets. So with our technique, we were able to transfer more data as compared to the original MOXIE technique, while maintaining the performance close to the MOXIE at high K. And like we were able to have 11% gain in spectral efficiency with our technique at high K, or I mean by K I mean the number of bits, at a data rate acceleration factor of 0.9. Yeah, I think that's it.
Okay, yeah, thank you for the presentation. Okay, so now is the question and answer time. And any question from the audience? And if you want, you can also type your questions in the chat. Okay, so I'll read out those questions from the chat. If you don't want to speak, speak out. Okay. Yeah, maybe I will ask one question first. Okay. For the simulation, if you go to slide 11, yeah, this one. So, what kind of simulation tools you are using for this simulation? Ayman, and can you answer this question?
For me, so you mean like, can you hear me?
Yeah, I think I lost you a little bit. Okay, now it's good.
Yeah, so you were asking about the simulation tool that I use?
Yes, yes.
So I basically use the MATLAB to kind of simulate all this.
Okay, so this is kind of common practice in this field, using MATLAB?
Yeah, I mean, yeah, I think it's kind of commonly used to kind of simulate this.
Okay. Yeah, another question, you mentioned that when the K is high, right, you have a better performance. But what happened for when K is smaller, and any other possible approaches to our any solutions for when K is lower?
So I think the possible reasoning for that is that when the case is small, so as because of the ISI, we need to because of the interference, we need to pick a lot of samples. And if you pick more samples, which means we will have the more noise. So it kind of deteriorates. So, but usually we don't transmit k equals to 7 bits. I just use that number for the purpose of the explanation. But if we have if I have a small k which is k equals to 7, and if I have to pick, for example, 19 more samples as compared to k equals to 7 because of the interference, so of course I will have the more noise. So that kind of could be the explanation that why performance is very bad at k equals to 7. And also we will have a lot of zeros as compared to actually the transmitted zeros. So that kind of degrades the performance.
Yeah. Okay, I saw one question from audience is from Ozan Guanys. Okay, so he asked on slide 11, yeah, same slide. What is the maximum number of the bits that can be transmitted?
So I think it depends how many I think we can transmit up to 200 bits, 300 bits. It depends how much bits the shard data packets is using. It depends how longer the data is. So yeah, I mean, I think roughly between 200 to 300 because that's what we assume that are transmitted in the shard data packets.
Okay. Any other questions from the audience?
Hello, Professor Lee. This is Rinku. Good afternoon.
Okay. Yeah, go ahead.
Yeah. Hi, Aman. This is a nice presentation. So I have a basic question. You mentioned about probably in the initial slides, figure number 1, 2 as well. So transmission and reception in the signals, modulation is required. So is there any effect of line of sight communication? I mean, did you consider any line of sight in this study? Is it needed to study line of sight here?
So basically, I assume, I mean, if we have if we don't have any, of course, if we have line of sight, so probably, if you are assuming that we don't have any received signal except the line of sight, so it means that we won't have any additional zeros introduced because of the channel. But here, I have assumed the worst case scenario when we have received a lot of copies. It could include the signal from the line of sight as well as the after the diffraction from the other objects. But if we only have the line of sight, so it means that we only have one tap channel, so it means we won't have any extra zeros. But if we have the line of sight and the additional zeros, so it basically does not matter because even though we have the line of sight, but the extra copies will the reflection from the other obstruction result in extra copies being received. So yeah, it won't affect anything, I think. The way this modulation is based on.
Thanks.
Yeah.
Okay. I think that's good. So yeah, we'll stop the Q&A at here, and thanks again for Ayman for the presentation. Okay, and then I'll just give a very brief comment on the content and the style. I think generally speaking, the slide and talk are very good. You know, you're very confident about your result, and you use the diagrams and show the result. That's very good. I just want to remind you one thing. Okay, so basically, before you give the talk, okay. So anyway, I saw that you're a master student, probably haven't attended the previous sessions in the seminar. So before you give the talk, you need to think about who are the audience, okay, and what's their knowledge level in this field, and then you really want to make sure that at 50% of your time, that most of the audience, not most, but many of the audience can still can follow you, and then they can learn something from this talk. Okay, so generally speaking, that in a talk is that 1/4 of time you give a very basic kind of undergraduate second year, first year, second year level, And then the second quarter of time, you can go up to like the third or fourth year of undergraduate student level, and then the rest of one quarter, the last quarter, you really want to show something that people working in this field. Okay, this rule normally apply to if you give a talk that people don't have the background. Okay, so for example, they are not working in this communication field, and so you really want to, for example, the first few slides, right? You're using one diagram, this eye diagram, and if people are not in this field, they really just get lost. You're talking a lot, keep talking about that eye diagram, but I don't think if people are not in this communication field, they will know too much about that. Okay, so very important is that because this E990 is not really only for communication, right? And so you really want to give some background. So make sure that the most audience can follow you at the middle of your talk, okay? And then they feel that, okay, they really learn something instead of quickly get bored and get lost, okay? Anyway, this is only for E990. My point actually is that in the future, because presentation skills are so important, okay? So before you talk, you always want to think, want to know what's who are the audience, what's their level. And the whole point of the presentation basically is that make sure that they can understand at least some of your talk, if not most of your talk, okay? And that's the general comments for the presentation, okay? Anyway, because you're a master student, right? And there's still a long way to go. But generally speaking, I think it's a very good talk. And also you can try to use a little bit more slides, right? And it's instead of just give one slide and you keep talking that, you give them a few slides, try to help you probably deliver the message, okay? Anyway, I think it's pretty good. Okay, I really like the result, and you're very confident. Thank you. Okay.
Yeah, thank you.
Yeah. Okay.
Topic today is displacement damage and the total ionizing dose at high and low dose rate performance of an opticouplers. The contents are include the introduction, background, experimental setup, testing result, and the discussion. Last one is the conclusion. First one, we have to introduce like the space radiation environment, because our topic is related to the device related to use in the spacecraft or satellite. So the component in the space radiation environment is so many, but mainly is two kind of particles we talk about today is directly related to my topic. So first one is transient particles, include galactic cosmic rays and hydrogen heavy ions. This hydrogen heavy ions is primarily result of nuclear synthesis, is kind of like even confirm the stellar evolution a long time ago, kind of. And the next one is solar particle events. And then the second main part is trapped particles. First in Earth and the planetary magnetic fields, and another one is more famous and related to us is Earth Van Allen belt. From the picture here, we can see here the small one, the small ball is Earth. Around here is a belt around the Earth. There's a trapped, this Earth Van Allen belts is mostly trapped particles or proton, electron, heavy ions. The second, because our device will put in the space environment, so we have to discuss the radiation effect, how affected by the radiation environment. So the critical area for the design in the natural space radiation environment, because sometimes not sometimes, always, we design in the Earth, like in our lab is good, but in the space, probably not good. So here is two concerns. First one is long-term effects. There include the total ionizing dose. We call that TID. Another one is displacement damage dose, DDD. In some articles, they call that DD. And the second one is transient or single particle effects. We call that single event effects, or SEE, just kind of see people see, which one can cause two kind of errors. First one is soft errors. Second one is hardware errors. So the first one is total ionizing dose. Actually, for those one is a little bit complicated. Depends the time, so I just quickly give a general presentation. Here is an instant particle can cause direct or indirect ionization of the semiconductor. The figure A shows the charged particle passes through a semiconductor material. The figure B shows the charged particle interacts with the semiconductors. Here, like a kind of, we'll show the result in the figure C. As the electron, we can see the electron and the hole pairs are generated along the path of the particle due to the energy, due to the particle energy loss. The last part is the result. The holes that are created remain trapped in integrated circuits oxide. Generally say is here is the like a gate oxide. The holes will trapped here, then will affect the performance of the semiconductor. The second one is displacement damage dose. This one is different. This one, the first one is just you lose its energy to ionizing the electrons or holes. The second one is related to atoms are displaced in the semiconductor lattice. Damage is caused by movement of the single lattice atom after primary collision. Because here is generally the first collision usually won't affect the semiconductor, but from the first collision, they will cause some second particles will cause this problem. So we can see here, instant particle get in and exciting the particles, and here will make some like a stable defect. So the several damage clusters are produced by the collision. And here, interesting thing is the low transfer processes produce more localized defect. And then the last one I want to introduce today is SEE. This means an instant particle acting on a semiconductor like a proton or a heavy iron. So the figure A shows a charged particle passes through a semiconductor and they interact. The B shows that electrons are generated by the particle as it traverses the material. So we can see here lots electrons here. And the C, we know the electrons are highly mobile and it will flow through the MOSFET, like this one is a MOSFET, and are collected at the reverse biased junction. So they will collect it to here. So the D, they will show that these electrons create a pause of a current shortly after the particles interaction. So this one will directly affect the device performance, like probably for the logical circuits, they will turn 0 to 1 or 1 to 0. So this is the problem. So now is the background. Why we study this with the optocoupler and we under the space radiation environment? Because optocoupler is small, but it's one difficult optoelectronic components that can cause even cause the spacecraft operating failure. Here is two examples. One is like a permanent damage occurred in one type of optocouplers on Topax Poseidon of about 2 years operation. This one probably we are not familiar, but the second one probably most people are know. It's one proton-induced transient in a different type of optocoupler caused a partial shutdown of a Hubble Space Telescope. I think most people will know the Hubble Space Telescope after upgraded electronics were installed in 1997. So this means is research for optocoupler under the space radiation environment is very important. Our experimental setup, the device under test, this optocouplers names FOD 817 is consists of a gallium andesite infrared emitting diode and a silicon phototransistor. Actually, between these two parts, like here, this part and this part, there has some kind of silicon stuff medium in between them for isolate them. So this is the 4-pin dual inline package, and then the current transfer ratio. This is a very important parameter for to consider his performance. From the datasheet is from 50 to 100%. And this device can be used for the power supply regulators, digital logic input, and microprocessor inputs. So it is widely used in spacecraft and satellite. The test facilities. This is not a big test, but we still need go to three facilities located at two different universities. First one in our UFS, there is 2 gamma cell 220. The high dose rate of this is 1.97 read silicon per second, and the low dose rate is 0.053 read silicon per second. And then another one, we have to bring the test equipment and the device travel to Vancouver. There is a high energy proton irradiation at the TRANF Proton Irradiation Facility, PIF, in UBC, University of British Columbia. The left side is gamma cell in UFS. The right side is PIF in TRANF in UBC. Here is still the experimental setup, the schematic of the test of Cobalt 60. Here inside here is a small device, and also we put 3 resistor as the voltage divider to get the best performance or the result to test. And the right side is used in TRANF for the proton test, because there is a radiation room, so we couldn't get frequently to change everything, so we have to set it little bit complexly for the test. Left side is the gamma cell chamber, and the other 2 pictures are in the TRANF. So yeah, there's lots of wires, connections, and even we have to do is in double in case one is failed, so we have to switch to another one. This test signal was 0.6 to 1.5 volts triangle wave, because from the previous research of the DDD and the TID effects, we found that mostly used static signals. So this is one innovation of this research. They can test it in the dynamic signal input and output. So this is the test result, and we can see the top and the left is the high dose rate with the cobalt 60. The top right is the low dose rate 60, and the right bottom one is the with the proton. So we can see this CTR. This is CTR include because it's the dynamic triangle wave, so they have reached the top bound and the bottom bound. They have a kind of a range for this. We clearly can see I mean, the figure shows the equivalent. Show this the degradation of CTR is follow the cumulated total dose. Actually, the previous research of Allen Johnston shows that the main radiation effect of the optocoupler is on the LED attenuation in the optocoupler leads to the emission reduction and the lifetime minority carriers in the photodetector, resulting in the reduction of the photoelectron collection efficiency. So to compare the comparison of the CTR performance of this, like if we directly use like these three pictures, looks like we couldn't analyze and find some details clearly. So then we use these three different radiation under these three environments. We normalization these CTRs with their initial values. Like from here, the beginning here is kind of from origin like the same unit as a whole unit 1, and the top, this red square and triangle one is the high dose rate. The empty one is the low dose rate, and the bottom one is the proton. We can see clearly looks like the high dose one is better than the low dose one, but the proton one is very decreased for the CTRs very badly. So these figures can show that the normalized CTR as function of equivalent dose after cobalt 60 and proton irradiation. It can be clearly seen that the current transfer ratio CTR gradually decreases with the increasing dose. The decreases in CTR is dominated by the displacement damage for the proton. So like I just mentioned before, the DDD was mostly caused by the proton. And the degradation can occur in two different ways, reducing the light emission of LED and reducing the minority carrier lifetime in the phototransistor, which causes a reduction in output collector current. But the main TID effect of gamma rays came from cobalt 60 is on the silicon phototransistors. So here is came from here, and here we measured in the detail one, we measured exactly the number, the data plot to put in this table. Is I'm not going to read this out because the presentation time, but we generally can get some like discussion. Like for a given ionizing dose of proton irradiation, the results shows a much higher, from the proton rate of degradation than the cobalt 60 irradiation. And also we can see that the CTR degradation of the device caused by high energy proton irradiation is more significant because, like I just mentioned, that is due to the additional degradation of proton-induced displacement damage. And the displacement damage mainly affects the emission of the LED. So this is the general discussion. And here also has some more, testing result is because this FOD A17 is composed of light emitting diode. I mean, this is LED made of a gallium arsenide material and a silicon phototransistor. The degradation of the device depends on the degradation of the LED and the phototransistor. And then the testing result shows the variation trend of damage caused by different dose rate or of ionization radiation is consistent and very close, like it decrease followed by the accumulated dose. But the damage caused by the proton radiation and the gamma rate of the cobalt-60 radiation is very different. The damage caused by the proton radiation is much greater than the damage caused by gamma rate. In the case of the proton radiation, the total degradation comes from ionizing and the non-ionizing effect, but the displacement damage effect, DDD, in gallium arsenide LED is more dominant. So the conclusion is the result shows that the device remained functional after 40 carat silicon of total dose irradiation. And we couldn't observe any SEE from the proton irradiation, even up to 2E11 proton per square centimeters. So therefore, the conclusion is this device can be considered using in orbits with shorter duration emissions. I mean, in the low orbit durations, because it's less some radiation effect. Yeah, I think that's for my presentation for today.
Okay, thank you, Zhu, for your talk. Okay, any questions from the audience? Okay, we have one question from the audience. So the question is, how many devices were tested?
Sorry?
How many devices were tested during the experiment?
For this case, we tested with the 3 other different brand and models optocouplers. But for this one, we only test 3, because first one is low dose, one is high dose, and one is proton. We only tested this one. And especially for this research and the test, this is a commercial device. We kind of randomly selected from the market. It's not hardened or designed one for specifically in the space radiation environment. We generally just for some research to get the opinion and make next step to how do we harden in that, how do we shield in this to avoid the effect to make those devices performance better.
Yeah, and then I have a follow-up question. So if you only test very few devices, how much confidence, the result will be similar to the other devices? I mean, can you have some elaboration on that?
There actually in our research, there's a kind of have some role is if we want to choose a specific device used in the space environment, we at least test it with, I remember the number was 11 or 13 devices. At least we have to test it is 13, the same one, same brand, even the same manufacturer, and even the same manufacturer batch, I mean the date. So we have to test them in exactly the same thing. But this one is not specific for using in just for general research.
Okay. Okay. So basically, this is just like for quickly screen some devices, and then you need to have some follow-up testing, right? If you want to really use for space applications, right?
Yes.
Okay. Another question actually is that I saw in the diagram you have the high dose rate and the low dose rate COVID-16 testing result, right? And then they have some differences, right?
Yeah.
Can you try to explain it why the low dose and high dose have some difference?
For the communicated total dose, I mean here is top one is high dose. Here the middle one is low dose. The total communicated dose are the same, exactly same, is around 40 crads, but the dose rate are different. So from here we can see that with the different dose rate, the results are different because there is there's a time difference and the dose rate difference. The red one, the high dose, was shortly, I think, just in few hours. The low dose one probably performs at least around 10 days. So there is one concept I didn't introduce today. There is a there's a, how do we say that? There's a sensitive with the low is enhanced low dose rate sensitivity, because this one we only observed a little bit sensitivity. This sensitivity of the enhanced low dose rate mean even we put that under the low dose rate, the environment, the effect or damage by the environment will be more significant than the high dose rate. But from this device, there is just a little bit of difference. So kind of for the saving presentation time and for the, is not very important for this device. For others, some like before we did some, how do we, power switch regulator, they are totally different, very significant. So we have to consider that. But for this one, generally we didn't consider that too much.
Okay, good, thank you. Yeah, generally speaking, yeah, the presentation is good. And the only thing I want to remind you is that in the future presentation, and you have to be a little bit sensitive to the time. Okay, so if you're given 20 minutes and you have to make sure that you can try to complete in 20 minutes. Okay. For example, yeah, if you go to a conference and the chair some chair may be very strict on that. The reason is that because there are a lot of talks, and if one talk have used more time than expected, and then the whole program will get delayed. And then, for example, when it runs to the noon time and people are eager to go for lunch, right?
Okay.
So yeah, so I have to make sure that try to do more practice and make sure that you are writing in the time that assigned to you. Okay.
Okay.
Yeah. Okay. Thank you. So.
everyone. So my name is Muhammad Ham, and basically this is a big project, and it's an ongoing project. And I will be presenting the first two phases of the project that have been completed. So myocardial infection detection is the phase one, and this myocardial infarction is another name for heart attacks. Okay, so the context of the presentation is that we want to detect myocardial infarction or heart attacks using edge devices such as smartwatches. And recently, if you've seen the Samsung Smartwatch 4 or Apple Watch Series 7, they include ECG capabilities. So we want to exploit those so that we can have an early warning system, like kind of an early warning system for people that are at risk of heart attacks or any sort of heart problems. Um, However, it is not as simple because uh, whenever there is any sort of heart complication, you don't have a lot of time to respond to it. You can see here we have outlined that in 20 minutes, the patient must realize he's having a heart attack. He must notify the emergency services. They will come and pick him up perhaps and take him to the emergency, for example, ICU or to some cardiologist, and then he needs immediate care. And all of this has to be completed within 20 minutes so that he must not suffer any sort of physical or like physical injury, permanent injury, or death even. So we don't have a lot of time. So if we can automate the first part of the process, which is identification of the heart attack occurring, and the patient doesn't have to call the services. So if we can automate that part, it can help in the mortality rate that I have highlighted here. That out of hospital cardiac arrest, only 11% of the patients survive to be able to discharge, and that's a very grim number. So we want to improve this number through this work, and that is the basic motivation or the idea behind this whole project. So in this book called The Chain of Improving the Survival Rate of Heart Attack Victims, they highlight that the chain of survival includes five important steps. And out of these, I've highlighted that the most important one is the step number one, immediate recognition and activation of the emergency response. Because everything else, the government has already worked to make it optimized. However, the first part is entirely reliant on the patient, not the patient, but the person that is suffering from cardiac arrest. And this step is going to form the core of our project. Okay. So just highlighting a few examples of the tech that are already in the industry. The Apple Watch Series 7 can take ECG at any time. However, it is not as good as the ECG machinery available at the hospitals, which usually uses the 12 lead system. Um, the Apple Watch does not have any sort of AI on board to detect heart attacks or even heart arrhythmias. They have a limited system on board which detects atrial fibrillation. It's a very specific heart disease, and uh, it is not that common even. So if we can expand this already available functionality, then that would help the consumers a lot. So moving on to how to fill this void, I'm going to talk about how the people in the literature have tried to tackle the problem. So this is a paper from a conference, and the highlights of this paper is that they don't use any pre-processing of the data. The dataset they use is an old MIT dataset, which has ECG data of about 48 patients. It is a 15 ECG lead data, but this proposed convolutional neural network only uses two out of those 15 leads. Now, coincidentally, these two leads also are very similar to the ECG system used in the Apple Watch and the Samsung Galaxy Watch 4. So this paper, even though perhaps they did not aim to be that relevant today, but this is a very relevant paper for our application. Their accuracy is 99.43% on a record-wise split and 97.83% on a patient-wise split. What this means is that because for every patient there are multiple records, so in a patient-wise split, they say out of 48 patients, we take 36 into training and the rest into test. And for record-wise split, they just shuffle all the data and then do the test validation and training split. So that's just the difference between those two metrics. So this is the structure that they're using. They have 1D convolutional layer followed by batch normalization layer, and then they use 8 of these. They use 1000 hertz sampling and 10 seconds of input. Now, this is not good because in Apple Watch and Galaxy Series Watch 7, this sampling rate is not present. They usually sample at 250 or 360 hertz. So we cannot take this algorithm directly into the Apple Watch or any edge device for that matter. Um, so just an overview of the result that they have. They're talking about the combination of the leads they used and which accuracy they got in table number 4 and in table number 5. And finally, in table number 7, they tell you what is the best possible performance they could get out of the system. This is their comparison with the other studies, but I just like to highlight that they got 99 point something percent in all 4 important metrics of sensitivity, specificity, and precision, which are our goal is to make sure we can maintain that our algorithm maintains some sort of a relative performance, but a much more smaller footprint, because you can see here the total number of parameters is 190,000. This much parameters cannot be loaded into the small memory of Samsung Galaxy Watch or Apple Watch or any edge device. So we will be reducing this number of parameters, and we will make sure that our accuracy and sensitivity are comparable to the work presented here before you. So moving on, this is our work from here on now. So we noticed that many neural networks or many frameworks, AI frameworks aimed at edge devices, they use a sort of a very triangular, if you can imagine it, a triangular approach towards the network. They start big, and then after detecting the big features, they start to increase the number of channels. However, they reduce the size of each feature map. So as you can see here, it expands in one dimension but is reduced in the other 2 dimensions. This sort of architecture is not being followed by the work that we have discussed before. So our algorithm takes this theory behind the architecture of neural networks and it designs a new neural network. So this is our, now I'm going to talk about our work. So this is the neural network that we have proposed. And here I would like to highlight that we are from here on out optimizing 4 hyperparameters. One of them is what is the total number of parameters in the network. The second of them is the window of the ECG that we are taking. Here we are taking 10-second window with 1000 hertz of sampling rate. So these are the 4 hyperparameters. Sampling rate, window size, total parameters, and 3 parameters. So in this network, we have 5 convolutional layers, and then we have our linearly connected layers, and then finally a sigmoid layer. So you can see that when comparing to the original, our version only has 50,000 parameters. That's 26% of original, and our accuracies are highly comparable to the work that we have discussed before. Now we went on to use a different form of hyperparameters where we instead use only 2.5-second windows instead of the 10-second window. And here you can see that our network is just the 9% of the original network, and yet we maintain, we got a very big hit in the testing accuracy, but our validation accuracy and training accuracy are very comparable to the original work. We even beat the network in the validation accuracy. However, we were not happy with the testing accuracy, so finally we decided to instead go for a very balanced approach where we use a 4-second window with a reduced sampling rate. So here the size is a little bit more than before. We had 9%, we got 13% of the original at 23,000 parameters. And here the testing accuracy that we have got is 95%, and the training accuracy is about 98%. This version of the algorithm, these metrics you are seeing, was actually tested on Raspberry Pi 3 using TensorFlow Lite, TensorFlow Lite package. So we use that to port this algorithm onto Raspberry Pi 3, and these metrics you are seeing are actually from an hardware device that running the algorithm in real time. So here you can see that we were able to significantly reduce the footprint of the network, which can actually run on an edge device with a very comparable performance, because we are not going for expert system, we are going for an early warning system. And for that matter, these numbers, we are really happy with these numbers. This is phase two of the project, where at first we have talked about just heart attack. However, However, this is not heart. Hearts are very complicated organs, so they have a lot more problems. So here we go for another approach, which has a wider scope. Here we are looking. Here our motivation is that we will train, like before, a CNN on a big data set. However, this time for every patient, we will also tune it a little bit on that patient's specific heartbeat patterns, so that it can better visualize, it can better differentiate between abnormal and normal heartbeats. And and this is the just an outline of the structure of how it will work. There will be a big CNN, and then it will use the dedicated data set to tune itself into the tuned CNN, which will be then used for the testing and the classification part of the problem. So here we are just going to visualize the data set, where you can see that there are 48 records of half an hour length, two-channel ECG recordings. This is different from phase one. The sample rate is 360 hertz. And there's some common challenges I've highlighted here is that there is a high sample rate for edge device deployment. You can see there is 360. We are aiming it to be 250. So we will resample the data. And look, in the graphs, F is called a fused beat. What it means is that on your left side, you can see a V annotation. So this is a ventricular subperfusion. And this, when this V classification is merged with an N beat on your right side, you can see this makes the F beat. So the algorithm, we will see further in the presentation, the algorithm really confuses the fuse beat with both the V and the N beat, because it has the features of both of them. So this was a very difficult problem to solve. And this is just, the data visualized here. And this was our approach. First of all, we decided to use an input size of 196. This was because after a 250 hertz sampling rate, we normalized the data to just take the middle section, and there are some noises at the edges of the ECG reading after the beat, so we get rid of those. That 196 came to be a very reasonable width of the ECG that we were willing to work with. Then there was a little bit of data pre-processing that was required, so not all annotations were of equal length. So we went and normalized the data. We resampled the wave. There is a very high imbalance in the data present, because as we can expect that the normal heartbeats overwhelm the samples of the normal heartbeats overwhelm the abnormal heartbeats. So we had adjust the data set to make sure that each class got an equal representation during training. Um, and finally, you can see that the split is unique to our application. There is not a train, validate, test split. Here the split is train, tune, and test. So the tune set is specific is a different data set for each patient, and this tune set is given to the network after the training phase, so that in tune itself just for that specific patient. So, for example, if I'm Hamis and I want this algorithm to work for me, the tune set would be the first 10 minutes of my ECG data. And then the algorithm would tune itself to my specific heartbeat patterns, and then it will start classification. So we will see how this tune, introducing this tune step into the process helps out improve the performance. So here is the general structure of the DNA network. As I am telling you that these phases are quite disconnected, and I will talk to you about how they all come together for this project. But this is an ongoing project, so please bear with me. So here we are talking about a completely different network than before. Here we have a general convolutional neural network, that is GCNN. It has 32 channels throughout. It has and there are two max pooling layers, and every convolutional layer is followed by a batch normalization layer. Here our focus is just to figure out whether this tune step works or not. We are not talking about optimizing the footprint of the network or anything like that. So the training and tuning parameters for the optimizer, we use stochastic gradient with momentum of 0.9 and landing rate of 0.01. Our training hyperparameters for apox, we went to 50, and we added a parameter that whenever loss is less than a certain value, the training is terminated, because we don't want the network to become overtrained, and so it becomes highly uh, biased towards the normal heartbeat. The batch size was 128, and we trained it over the common dataset. And this network, after training, is called General Convolutional Neural Network, that is GCNN. Then this GCNN is taken to the tune set, and on the tune set we used same stochastic gradient descent and a very limited epoch and loss setting so that the network can quickly converge. And after it has been tuned, this GCNN, we call it TDCNN, or Tuned Dedicated Convolutional Network. And you need to realize that we just take the first 10 minutes of ECG, so the number of samples are different in each patient's tune set. For example, my resting heart rate might be 61, and someone else's resting heart rate might be 70. So the sample rate of my tune set would be much less compared to the second guy. Okay, so the results. Oh yeah, the evaluation approaches. So we use the main approach, that is basically, we say that from a consumer perspective, if I'm a person and I'm looking at this application, I want to know whether my heartbeat is normal or abnormal. It doesn't concern me that which type of abnormality it is. I just want to see if it's serious, then let's call the ambulance and I'll have a talk with the doctor who is really expert in the system. The secondary approach is that of a computer science student that might be interested in what is the FL score of the network, where is the network being confused, and so forth thing. So we will just follow the main evaluation approach for now. So these are the results. And just to highlight, the GCNN has 89.32% accuracy, and the tune dataset. Now here we are talking about a baseline. The baseline here that we are talking about is a method that they used to use before. This is a proposed method before the advent of artificial intelligence, where they use simple signal processing to figure out whether the heartbeat is abnormal or not. And as you can see, for each patient, we significantly outperform this machine learning approach, you can say, in our, now this is TDCNN A1. This is approach 1 from the consumer perspective, where we have two classes, normal or abnormal. This is binary form. And in TDCNN A2, there are 5 classes. So we are just talking about A1. So in A1, we significantly outperform the baseline for all patients. Moving on, this is our result for every patient that was included in the test set. And you can see that at the end, we were able to achieve 96.6% accuracy. And this is the end of phase 2. So in phase 2, we were able to figure out that we were able to increase the accuracy from 89% to the 96% using the tuned step. So in phase 3, we're going to combine our phase 1 and phase 2, the heart attack and heart arrhythmia parts, and take this tuned setting onto an actual edge device, and then figure out whether this actually works when implemented in the field. So thank you, and I think that's the end of the presentation.
Okay, yeah, thank you for the talk. And any questions from the audience? Yeah, so it's the last talk. Probably people is a little bit tired. Okay, I just one question actually for the edge. You're talking about this edge device, right? Do you have something in mind? What kind of edge device you want to implement?
Professor, right now we are working with Raspberry 3 and 4s. However, the target application would be something like Raspberry Pi Zero, because we want to see, because the Apple Watch and the Samsung Galaxy Watch 4 use dual core processors. So we want a dual core processor board where we can this application. Right now we are using quad core Raspberry Pi 3 because of the shortage, that the global shortage, the Raspberry Pi Zero is not available. So our target is Raspberry Pi Zero, but we are slowly working towards that. Any dual system would work.
I just wondering that I see actually this is really good application, because it's a very real threat, right, to all the people who could have the heart disease, right? I mean that. Do you think it's possible how in the future that this kind of algorithm can be implemented, for example, into the Apple Watch, something like that?
Yeah, it is actually very possible because Apple is slowly taking those AI, there's neural network engines, and they are building them into smaller and smaller devices. So it's quite possible we can see a neural network engine in the Apple Watch. And if we get that hardware, then running an algorithm of this size or even a bigger size will become quite easy.
True. Okay, good, very good. Yeah, I think the talk is very good, and I really like I think you have this motivation, right, to tell people what's going on, everything. I think that's very good. The only thing is that the content is a little bit longer.
Yeah.
31 slides, and then sometimes then you have to talk very fast, right, so that you unless you put, for example, put some slide even as appendix, okay, after the, and then if people ask that question, then you can bring up those slides, okay. So then, yeah, that's also another type of the skills in the future you always have to deal with, is that how to select the slides, okay, how to select the content. You can try to maintain the flow at the same time, because you have, for example, there are many details, right? I can give you 5 hours, so you can still keep talking, right?
Yeah.
But the problem is that how you have to select the material that's most important, okay, to deliver the major message, and then you can leave some details that for the Q&A session,
Okay.
because someone, if they're interested, they have done some similar work, definitely they will ask you about some details, and then you can address specifically for during that time. Okay.
Yeah, makes sense. Thank you.
Okay, good. I think today, I think our session is very smooth, and actually I'm pretty happy that for today we will have a relatively good, high quality of presentations and slides. And thanks at the end of this session. I would thank you for everyone attending this one, and spend some time to listen to our young researchers, right? I think that's actually it's exciting time, for your research program. And I also want to wish that you have the success in your research program. Okay. I think then that will conclude our session for this seminar. Okay, thank you. Have a very good weekend. Okay, bye.